Ladies and gentlemen, welcome to the ICE-JLA meeting, working platforms for pioneering and track. This event is brought to you by the Institution of Civil Engineers. My name is Novan Bennett. I am a student from Yunus University, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinar. After that, the event will start with opening remarks from Phil Mency as the representative of ICE-JLA Association, and then continued by Mike Downey, who is also the representative of ICE-JLA Association. As our moderator, we'll start the presentation of our supporting speaker, Anggita Priscilia, and later will be continued by the main speaker, Stephen Buttling. The event will then continue with a Q&A session. Now, ladies and gentlemen, for your own convenience, please pay attention to the following rules. You can ask your question to the speaker by pressing the raise hand feature located at the bottom of the screen. The question should be in English. You can raise your question after the presentation of the speaker. Now, I would like to invite the representative of ICE-JLA Association, Phil Mency, to give his opening remarks. To Phil Mency, the time is yours.
Okay, thanks, Marvin. And first of all, welcome everyone. Those present here at EB and everybody online. I know we've got quite a few that have registered online, so welcome to everyone. We've got a few new faces or faces that used to be involved back with us today, so welcome to everybody. The committee has already been very busy this year. I'm pleased to say that we've got quite a lot of really good quality presentations for this year. Tonight's is our first. In keeping with something we started last year, we've actually got two presenters. The first one is from the University, Venus, and the second, our main speaker, is we'll be talking about temporary works, particularly working platforms. The two are both very closely related to a geotechnical subject, which is close to my heart, and obviously to Magnolia. So I'll let Mike step up and introduce the speakers and the topic.
Okay. Thank you very much, Phil. Also, a welcome from me to everybody here tonight. We have a growing audience for the live part of our event. We're also showing this one online as well, which means that people from further away can join us. So it's certainly nice to see more and more people gathering here at our regular venue in the Eastern Province. So I think that we have two speakers tonight. It's quite interesting actually that they are quite different in their years of experience, and it'll be very interesting to see what you learn from both of them, because I think they both have some interesting information to tell you. I mustn't take too long because of the two talks tonight, but so just briefly, our first speaker is Anggita Priscilia Sulistio. Yeah, we just call that Angie, much easier, Angie. And she's a student at Venus. Venus is a university that has an ICE student chapter. And we've been interacting with Venus now for many years with our Jakarta Local Association of the ICE. And it's given us a very rewarding interaction with students from Venus over many years. So Annie is one of these students, and she is going to talk to you about the revitalization of tourist ports in West Java. And it's going to be rather interesting, this, because I think it's going to be something that's very important for the development of Indonesia. So, Annie, can I ask you to take over and talk to us about your topic? Thank you very much.
Okay, good evening, everyone. First of all, I want to express my gratitude for these opportunities for me to able to present about my recent study about revitalization of tourist park in West Java. So recently, I did a research about park structure in West Java with the background because we know that Indonesia is one of maritime country, and West Java located at the most west area in Indonesia. In this port, located perpendicular with Indian Ocean, which affected with the high rate of wave high wave, and this port has been constructed since 2017 and has been done at the end of 2018. But as you can see in front of you, in year of 2019 there is a total of occurs because of sedimentation from the wave. In year 2020 up to 2021, the Tombolo covering the area of the port, and this led into that the ships cannot be docking in this port, so the revitalization is needed to be conducted so this port can be used again. The objective of my recent study is to determine the variation of lateral force in the port structure, and also determine the deflection of the pile and satisfactory value for each working phase. The limitation that I was at for this study is determined based on SFE 8460 in year 2017. And the deflection values is carried out using Flexis two-dimensional software. Based on the provided data, and the ship specification is a yacht vessels with a size of 15 up to 30 tonnage gross tonnage. And the ship specification average passenger capacity of 16 people. So here is the methodology I was used for this recent study. I was doing the literature study and collecting the data and then modeling the structure with Flexis two-dimensional. I did the verification deflection values according to the criteria from SNE 8460 in year 2017. And if the value from the set is not meet the requirements from SNE, then I am doing the reanalysis by changing the dimension of this ship. So here is the actual condition in West Java Port. Here on the water picture, there are the breakwater structure. On the picture, it is not actually a beach, but this is a tombolo created occurring because the sedimentation from the wave. And here is the alternative design that is proposed for this port structure. I was recently did the analysis in this square area, which is the most extreme area, with the depth of the sheet pile of -10 meters. Here I was doing the analysis with the software from ICE-JLA, which is software that is used for analyze the deformation and stability in geotechnical engineering. And actually, present two-dimensional, it's used usually for excavation, embankments, and foundation tunneling, such as mining, oil and gas, and etc. Here is this data for the ship's certification. As you can see on the screen, and the standard certification used is the first standard KPF 200H. And I also did the calculation for the soil certification, which is the soil parameters found is there are 4 types of soil layers. So this soil parameter will be input to access to dimensional. And here also the data for the height of the wave height, which is the yearly periodic use is 2025 year with the highest wave of 5.7 meters. I also determine the horizontal coefficient of the earthquake found to be 0.284. And this is the load applied in this structure. There are area load of 30 kilonewton per meter square, and mooring load of 50 kilonewton per meter, berthing load 50 kilonewton per meter, and wave load of 100 kilonewton per meter. In this modeling, in practice, usually we use to determine. Firstly, we have to determine the working phases. So here I'm doing the phase is by filing this sheet file and then continue it up to placing the truck. Next, I also did the load phases such as light load, wave load, mooring, berthing, and next I also input the safety factor phases to determine the value of each working phases safety factor. After doing the analysis with classic two-dimensional or the sheet file, there is found the deformation mass was and total displacement was 0.0198 meters. Here is the bending moment result for the left side of the sheet file and the right side of the sheet file, as you can see on the screen. Here also the value from the deflection result found it to be 0.003 meters, and on the left side is 0.015 meters. And this value still under the required standard, so it is still safe. And here I showing to you the most extreme load, which is wave with pipe load, and the safety factor value is still higher than the 1.25, which is safe, and for the berthing phase also still safe. So from my recent study, I did found that the value for the deflection many moments, and the safety factor for each working phases still meet the requirements and still safe. And I also found that the dimension of the ship file used was CCSP 600, and it is still shown that the file conversion is still good. Thank you.
Very much. I think it's probably better if anybody would like to ask a question of Angie, now is the right time, because her presentation is fresh in your mind. So maybe one or two questions for Angie. Anybody got some things they would like to ask? Yes, Mr. Trevor Simon, it's on you, but you're going to have to speak in here so people can hear. Sorry, Trevor. Sorry, we have a question. Trevor, if you could like to come and speak into the microphone.
It's just a simple question, I mean. I think the word tombola.
You have to come here to be seen.
So actually, tombola, as you can see from this image, did you see this is the fourth structure? This P section, yeah, and there is a sedimentation like this area.
That's a special word for sedimentation.
Actually, I don't
I
know.
haven't heard of it either.
I've heard of tombola, which is a fun fair. I don't know what a tombola is.
Also, we this area, sedimentation area. Yeah. Tombola.
David knows.
Oh, you know.
He's a waterman.
David, would you like to say something about this interesting work? You're over here, please.
My understanding is that tombola is a circular shape caused by tidal currents. I could be wrong, but I would like to ask a question while I'm here. I mean, it seems to me that the big problem here is sedimentation. There are various models for coastal sedimentation, and I just wondered if you thought about using a coastal model that model the movements of sediments within a harbour. Once you start putting infrastructure in the harbour, you create different sediment patterns. Right? I just wondered if you thought of using a sediment model. I hope I haven't put you on the spot here.
So actually, the first structure is not designed from. Actually, did the redesign because the first structure is considered to be failed, right? Because there is a tombola, and I think if you put the breakwater perpendicular from the wave, I think it will be safe and there is no sedimentation that will be occur in the future. Yeah.
Thank you, it's good. Okay. Andy, thank you very much for your presentation. It was very nice being theory, it was well illustrated. And if anybody else has questions, Randy, I'm sure we can track her down after the next presentation and discuss any points with her. So now, if we can get ourselves ready, I would like to switch over to our second presentation today. So, okay, are we ready? So I'm just going to talk to the team down here. Okay, right. So Actually, I'd like to say a few words, because you better not. Mark Paul Robert Tingay is not our featured speaker. Sorry about that, Stephen. It's if you'd like to be, we can arrange it.
I'll tell my mother.
Okay, I'll show you people here. Right. This is the risk of copy and paste, you see, on old slides. We all know. We've all made those mistakes, not just the team down here. Hang on, Reefa's busily typing down there. Right, okay. Just to let you know, Steve, in fact, he was our previous speaker. It was a very interesting one about the Lucy mud volcano. I don't know if you remember that. It happened here quite a few years ago. Maybe roughly the time you were here, I think. But yeah. I think we're almost ready now. Okay. Almost there. Okay, I think we're just about. Yep. Right, okay. Professional geomechanics, interesting. Okay, let's now be happy with your with this summary. But you know, a great pleasure to introduce to you Dr. Stephen Buttling. He starts off by mentioning many years of experience. In fact, in the notice here, he mentions 50. But what I would like to mention is that I've known him for about 50 years, because when I was an undergraduate at Bristol University, Stephen was a postgraduate. And he had the pleasure of supervising things like tutorial sessions and laboratory sessions and so on. And in those days, he had a pretty large red beard, as I remember, typical kind of postgraduate thing. But anyhow, this was many, many years ago. And after graduating and obtaining his PhD, he got involved principally in foundation work and cementation in the UK. And then he moved into the Southeast Asian and Asian area. And he's worked in quite a few different places. He had quite experience in Hong Kong, then also in Singapore, both to do with the mass transit systems, and then also in Thailand. And in Thailand, he set up his own consultancy for a time. I'm not sure if it's still running. He might mention that. But and then more recently, he moved to Australia and lived in Brisbane. And it's very nice from my own personal point of view, because we keep kind of tripping over each other from time to time, which is very nice. He also spent a few months working here in Jakarta, I think just before he went to Australia. And he may have attended one or two of our IC events in those days as well. I'm not sure if he did a presentation, maybe he did, but he might remind us about that. But anyhow, so that's probably enough of me rambling on. But amongst the things that Stephen has got involved with, very much so, is issues related to piling. And he's become very involved in the issue of working platforms for basically for tract plant. And this is a temporary works structure, if you like, as regards to civil engineer. And I think sometimes people don't give it too much of a worry. You know, it's a temporary works. You put down some stone of some sort, and you run your big heavy cranes over the top. It's bound to be okay, isn't it? But I think what you're going to learn very soon is that that's not how these things should be regarded. They're carrying very heavy loads. I mean, some of these cranes can be huge, and they're getting bigger and bigger and more top heavy. And therefore, a proper design and appreciation of the risks involved with a working platform is extremely important. Anyhow, so that's enough for me. I'm looking forward to hearing this presentation. So Stephen, I will hand over to you. and hopefully it'll go smoothly. Thanks very much.
Thank you, Mike. So I hope that you can now see my screen. Is that right, Mike?
It's very clear, yeah.
Okay, all good. Right. Well, thank you very much for the introduction. And I'll basically get straight into it because I've got quite a lot to cover. I did run 2 webinars in Australia at the end of 2022 and the beginning of 2023. The combined length was somewhere between 3 and 4 hours for the 2 webinars, and I'm trying to squeeze it all into 40 minutes. But anyway, so we'll get straight into it. One of the things, I had some recent experience in Penang, and I am not familiar with working platforms in Indonesia. But what I found was that in Penang, in Malaysia, the practice is quite different, and it seems that main contractors generally try to make the piling contractors responsible for the working platforms, whereas in the UK and in Australia, and I believe in New Zealand, normally it's the main contractor who is expected to be responsible for the working platform. There are reasons for that, and we'll come back to those either at the end or in questions, depending on how time goes. So this really, my talk here is starting in about 2004 when this incident happened, and a CFA rig tipped over, brought down the catenary cables for the part of the London to Paris railway line going through the Channel Tunnel. And of course, that cut off the power, so no trains came past. But just try and imagine if a high-speed train had been passing there at the very moment that that piling rig came down, and it's really quite hard to imagine what the consequences would have been, but they would certainly have been disastrous. And it was this incident that actually led to a lot of the work which I'm going to talk about. Now, I have got a couple of other examples, but we had problems trying to get the video sorted out. So I'll brush over these now and we'll come back to them at the end. So I've got some illustrations as to why this is very important still in 2024. I'm going to touch on how we calculate the rig bearing pressures, but I'm not going to go into that in any detail. That's normally done by the piling contractor. I'm going to touch on some issues of whether the main design method is conservative or not. And I'm going to talk about that main design method, which is referred to as BR470, which is the catalogue number of the BRE report, which describes the design method. They also did a review of it 7 years later in 2011, and I'll make mention of that. I'll also talk about the Temporary Works Forum of the ICE, which has produced a different design guide. And I'll make some mention of the T-value method, which was produced by Andrew Lees, who is a consultant to Tensar. And of course, Mike knows Tensar very well and has written some papers on that subject. I'll talk about the calibration of design methods, the importance of selecting parameters, and some work by David Cork and others in the UK and by Andrew Lees. So just briefly touching on how to calculate the track bearing pressures, there's only one way that I'm aware of that is readily available, and that is the FPS rig track pressure calculation tool version 3. And I emphasize version 3 because that's the only version that should be used. I found an error in version 2 back in about 2021, and it's been corrected in version 3, but version 2, where it's around, still contains that error, so it should be deleted. Version 1 is way out of date now, although people are still using it. So that does this work for you, and I'll talk a bit about that, but there are other methods. So doing it from first principles, you can use Euronorm 16228, but that's fairly hard work, as I say, doing it from first principles. And there's a very simplified method called the Austrian method. The coding is RVS 082102. And one of my colleagues, David Cork, is in the process of producing another method which is more rigorous than the Austrian method, but still very simplified. So you need to use one of these methods, and I certainly use the FBS spreadsheet, and it's the one that I recommend. So moving on now to the design method, it's all contained in this BRE report, BR470. But there have been suggestions, particularly in Australia, from some people that I know, that it's conservative. And I'm quoting from a written document that I have a copy of, where one of the designers said that we have not followed the BRE method for this platform, as it is known to be highly over-conservative for granular subgrades. And his manager actually sent me another message, which I have in writing, where he said, the typical view of most practitioners I met and discussed the issue with support the view that BRE is conservative. And yet, in spite of these two written statements, I tried very hard to get people to tell me, what is it about BR470 that is conservative? In the method, which step do you consider to be conservative? And by comparison with what are you ranking BR470 as conservative? And I have not been able to obtain any answers to either of those two questions. People are happy to just bag the method or blag the method as being over conservative, but will not actually provide any evidence to support their point of view. So going back to what we're trying to do, we're trying to design a working platform to support a piling rig or a crane. And we can do it using the basic principles of soil mechanics. We can calculate the bearing capacity of a layered soil. There are ways of doing that. The textbook by Bowles has means of calculating the bearing capacity of a layered soil. Be careful, because there's a printing error in Bowles, but it doesn't affect using the calculation method for surface loading. The error is with regard to loading supplied below the surface. So as long as it's a surface loading like a crane, the equations in Bowles will be okay for you. But the BRE chose to use a method based on punching shear, and I'll talk more about that in a moment. But we also now have the temporary works forum method, which is different, and the t-value methods. So in the BR470 design process, as always, we need a geotechnical model. We need to define our geotechnical parameters. And for the platform, these are the weight density, gamma. A lot of you will probably still call that unit weight, but I've gone away for unit weight in following the lead from Europe, because the unit has no meaning. And what we now tend to call it, we use weight density for gamma, and we use mass density for rho, because those better describe what the actual parameter is. For the platform, we also have an angle of friction, phi dash, and we have the subgrade. I'm going to concentrate this evening on cohesive subgrades. So we're talking about an undrained shear strength. And the BR470 method is only applicable for soils greater than 20 kPa and less than 80 kPa, where a working platform in many cases will not actually be necessary. If your subgrade is weaker than 20 kPa, you need to be very careful and use the better, more reliable design methods. So in the design process, we look at two loading cases. And load case one is where if the rig is about to tip over, there is nothing that the operator can do to save it. So these would be if the rig is just standing there and it starts to fall over, the operator hasn't done anything, so there isn't anything that he could do to prevent failure. Typically, if he's just traveling across the site, there's not likely to be much that he can do to prevent a failure. And if he's lifting something, such as a casing or a rebar cage or a precast pile, he's not going to be able to put any of those things down fast enough to prevent a failure. So all of those are referred to as load case one. And the alternative is load case two, where the operator can do something. And typically these are where the operator is applying a force, either a crowd force, a downward force, say to install a casing or a drilling tool, or an uplift force or extraction force to try and pull an auger, a bucket, or a casing out of the ground. And if either of those is producing instability, causing the rig to tend to fall over, basically the operator can ease off on the throttle, stop pushing down or stop pulling up, and the problem will be mitigated. It's also just about possible if they're traveling or slewing and either the mast foot or the load itself, suspended load, is sufficiently close to the ground that it can be put down to prevent failure. Not necessarily quite as easy as just easing off on the throttle, but those are considered to be load case two. In the design process, the bearing pressures are generally not going to be a uniform pressure along the length of the tracks. They'll typically have a higher pressure at one end and a lower pressure at the other, like Q2 and Q1 here, giving a trapezoidal bearing distribution. And if the rig starts to tip more, Q1 can go to 0, and we get a triangular distribution. Both of those are very inconvenient for calculation purposes. So what we tend to use is the Meyerhof approximation, where the trapezoidal or triangular bearing pressure is approximated by a rectangular bearing pressure. And the criteria are that the area under the trapezium is equal to the area within the rectangle, and that the centroid of the trapezium is in the same position as the centroid of the rectangle, as illustrated in that slide. And the geometry will tell you then what the relationship between the effective pressure Q dash and the pressures Q1 and Q2 are. That then will give us two uniform bearing pressures. Case one, a smaller pressure over a longer length, L1K, and case two, a higher pressure over a shorter effective length, L2K, with the track width, WK, being the same in both cases. So first of all, we say, is a platform required at all? And we check if the subgrade alone can support the track load. We do a standard bearing capacity calculation, and for case one, where we can't do anything, about the putting the load down, we use a load factor of 2. And for case two, where we can put the load down, we use a lower load factor of 1.5. And if both of those are okay, all we need to do is provide a running surface, a crushed rock surface, probably at least 150, maybe 300 mil, to stop the crane tearing up the platform when it's spragging, but a working surface is okay. If they're not okay, then we need to design a working platform. And the first thing we have to do is check that our platform material that we're proposing to use is good enough to provide the necessary bearing capacity. Now our load factors have come down from 2 to 1.6 and from 1.5 to 1.2. And that's because we were using 2 or 1.5 for natural ground. And we know that natural ground is very variable. It has spatial variability. But it's considered that a working platform, being a man-made platform with imported material that's been spread and compacted and tested, is more uniform, more reliable than a natural soil deposit. So we have lower load factors. But if those are okay, then a working platform can be designed. If they're not okay, then we need to get a better material for our working platform. And that basically means a higher angle of friction fide ash. And if they are okay, then we go ahead and we determine the thickness of the working platform. The BR470 process relies on what we call punching shear, because we've got this whole question of what happens under this loaded area through the granular soil. Many of us will be familiar with load spread, but there's a lot of debate about what the angle of load spread should be, and lots of different ideas. BRE decided to avoid those by using a vertical shear surface and calculating the punching shear on pushing the rig track down through the granular platform, and then a log spiral type failure surface in the underlying subgrade. This again shows how you'll have a lateral earth pressure against that vertical punching shear surface and the sort of distribution of side shear that you might get. So the BRE determined this equation where D1 is the platform thickness. And then the numbers that we put in are WD, which is the width of the track, Q1D, which is the design value of the bearing pressure, the undrained shear strength, the bearing capacity factor, and a shape factor, all to the power of a half, and divided by the weight density of the platform, the Kp tan delta of the platform, and a shape factor for the platform. And we do this calculation knowing all of these values on the right-hand side. We can calculate the required thickness. We check that the platform is at least 30 centimeters or half of the track width, whichever is the less. And I am quite certain that this is where the calibration of the BR470 process was carried out. And that is an absolutely vital part of the process. So what I am quite certain the team at BRE did was to use more rigorous calculation methods. Could have been finite element methods, could have been analytical methods, or both. And for a whole range of different piling rigs with different track widths and different undrained shear strengths, they calculated what the platform thickness would be, and they put all of those into a table. And then they gave that table to a panel of very experienced piling contractors in the UK and said, for these piling rigs, based on your experience, do you think these working platform thicknesses look about right? And there would have been some editing in that process. So they then ended up with a table, and I'll show you an example of it shortly, of values for D1. So then they will have gone back in using their particular rigs with values of WD, the undrained shear strength, NC, and the platform parameters, and calculated what the value of Q1D, the design value of the bearing pressure would be, and use that to determine what the loading factor is, because Q1D is the loading factor times the characteristic value of the bearing pressure. So knowing what the working platform should be, they've calculated what the loading factors would be, and that's how they've calibrated that these factors of 1.6 and 1.2 are okay to give the required platform thickness. So in the back of the BRE report, BR 470, it sets out in detail how to do these calculations. And I've made them into a spreadsheet. It's fairly simple. And there's the undrained shear strength of the platform, the subgrade. There's the chosen friction angle for the platform. There's the platform weight density, and here we have the track details, the track width, the bearing pressure length that comes out of those diagrams that I showed you earlier with the thin long rectangle and the thick short rectangle. These are the pressures for those, and when you put those numbers into the spreadsheet, down at the other end, well, this wasn't a very good example. So let me just change. Let's change that to 20. And we can now see straight away, we're needing a working platform. And in this case, the case 2 load is giving the more critical case, despite the fact that its load factor is lower. And we're needing a 990 mil thick platform for that case. We in the BR 470 method, there is an option to look at geogrid reinforcement. It's very crude, it's very simple. It only looks at the tensile strength of the geogrid and uses that to reduce the applied bearing pressure. It's very generic. You can use it as a guide to see whether a geogrid reinforced platform might be beneficial, particularly if you've got some idea of the unit cost of the granular material that you're going to use for the platform, and if you've got some idea of the cost of your geogrid delivered to site, because those two are going to vary from one site to another. Where particularly sort of on a remote site somewhere where it may be very expensive to bring in good quality granular material, you may well find that geogrid reinforcement has a cost benefit. On the other hand, in a site where good granular material is readily available, and maybe you're paying significant transport costs, import duties, and so on for geogrid, it's less likely that there'll be a cost benefit. This is really just a crude tool to give you an idea. And if it looks as if geogrids are beneficial, you're best off to go to your geogrid supplier and get them to do detailed calculations with their own method. But I'll come back more onto that later. So that, okay. There's a very similar calculation. I won't go into it in any detail now, but for granular subgrades, so now we've got phi dash to the subgrade, and we've got the weight density of the subgrade, and again the track lengths and widths and the bearing pressures, and in this case we need about 1.65 meters. Load case 1 in this case is critical, but we can calculate a required thickness. And again, we can quickly look at whether a geogrid might be beneficial. So moving away from BR470, in 2019, the Temporary Works Forum of the ICE produced this guide. It's not specifically related to piling plant. It's all construction plant, and it includes haul roads and so on. So it's a rethinking, but it runs in parallel with BR470. BR470 is mentioned within the guide. So this is the sort of a typical load spread model that I referred to before, and it's this angle beta that there's a lot of argument about. And what it does is affects the distribution of the actual applied bearing pressure. There's a schematic average bearing pressure, but that's an idea depending on the stiffness of the subgrade and the stiffness of the track as to what the distribution might look like. Elastic theory is used, and again, so this is perfectly elastic materials. A plate of diameter 2b has different bearing distributions, bearing pressure distributions, depending on the stiffness. So if the plate is rigid, you get this distribution that's minimum in the middle and a peak value at the edges. And if this pressure is much more elastic, then you will start to get a distribution similar to this, according to elastic theory. In a real clay, if we've got a rigid, if this foundation is rigid, then the contact stress will look like this. So we'll get peak stresses at the edge, and our deflection distribution will be consistent, uniform under the rigid foundation with some settlement profile at the edges. If it's a flexible footing, then we'll get our traditional saucer shape. If it's a real sand, the opposite happens, and we get these sort of pressure distributions. We've still got a peak at the edges where these sort of cut into the soil, but it's not as exaggerated as with the clay foundation. So within the TWF manual, they give this diagram for the punching shear model, which is very similar to what I showed you before. And they talk about methods that may be used for unreinforced platforms. And they talk about the TWF method, which can be used for all subgrades, and BR470 method for soft to firm, cohesive, or granular, but only a single layer. So there's only 2 layers in the BR470 method: the working platform itself and the subgrade. And a third option is a Syria report from about 1993, I think, that's called SP123. Again, it's only a single layer and soft clay. I have not actually spent any time looking at that method. And then for reinforced or stabilized platforms, the design standard is BS 8006. And there's a very simplified approach in BR470. There's something in SP123, but I would expect you normally to be using the manufacturer's methods, which are, of course, not codified. So this is what the displaced form is likely to look like with a loaded track on a granular platform. And this is the assumed failure plane in punching shear based on the work of Professor Hanna, whereas the actual failure planes are out here somewhere. But of course, there's probably no shear on this failure plane because it's going to be in tension, whereas there is shear on this assumed failure plane. This is a sort of failure pattern that you might expect due to the punching shear model. And again, these can be put into a spreadsheet. So this is the spreadsheet for the cohesive soil. Some of you clever people can find a better way of doing this than me, but it requires an iterative process. There are charts, and these are examples of the charts that are provided in the TWF method, and you have to pick numbers from these charts. Obviously, trying to do that in a spreadsheet is a bit difficult. I know some people have actually fitted curves through each of these lines on here, and that allows them to generate a spreadsheet which will just do the calculations itself. I'm not that clever, so I use the spreadsheet as the background in this chart, and I have this is where I need to put in the platform thickness. So this first bit up here is checking is the subgrade strong enough, and we can see that the utilization is 3.6, which is well over 1. So no, the platform, the subgrade on its own is not strong enough. So now I've normally put in a value of 0.3, and if I well, the first thing I have to do is I have to move this point up to coincide with the curve up here. So that's going to be about 0.95. What happened there? Oh, sorry, it's just gone and decided to right. Okay, sorry about that. So I'll try and put 0.94. Hope it doesn't reset. Yeah, okay. So that's just about lying on the line. That one's near enough on there. And when I come down here, oh, the numbers are so far out, it's not even trying very hard. So, okay, that number is far too low. Let's try 1.2. Right, that's now moved me over here. So I've got to put in a value of about 0.4, 0.7, somewhere around there. That one's not too far out. But utilization 1.17, greater than 1. So I'll go to 1.48, I think. It puts me over there. So I've got to get to about 1. Right, and now I'm right on 1. So that's a very very well designed limit state design, because my resistances are equal to my actions at the ultimate limit state. But that's factored loads and factored strengths, so that's just about okay. So that's the process that you can go through, and you have to check load case 1, you have to check load case 2, which I have done, and I've got the load case 2. I've got 1.38, so load case 1 is going to govern, and that can all be done. Okay, So, and again, the same sort of thing can be done, but this time with granular subgrades. It checks whether we need a platform at all, and then we have to put in a platform thickness, adjust this cross to lie on the right L over B curve, which is coming from here. So we're saying L is 3.6B, so we want to react somewhere near 4. And by the time we follow through, we get 0.98, which is very good, 98% utilization. So though that's the TWF method. Moving swiftly on to the t-value method, which is based on a lot of work done by Andrew Lees, and it's now been adopted by Tensar, and I think it's within the Tensar Plus and available on their website. But Michael, correct me, I'm sure if I'm wrong. Oops, sorry. So it's based on looking at applying a pressure over the width B through a granular layer onto, in the first publication, a cohesive subgrade. And what Andrew did was to get hold of the results of about 60 centrifuge tests that were published by Okamura et al. And he analyzed these using the finite element method, did a whole lot of numerical analyses. And what he found was that there was a linear relationship between the increase in the allowable bearing stress, or the ultimate bearing stress, sorry, the increase in the ultimate bearing stress, described as the ultimate bearing stress that platform can support, compared or divided by the bearing stress of the subgrade. And there's a linear relationship between that and the ratio between the platform thickness and the footing width, H over B, for infinitely long footings, strip footings, or between the bearing stress and the the square root of the bearing stress and H over B for square or circular footings. And the gradient of that straight line, T, Lees describes as a load transfer efficiency factor. So based on the Okamura results, this was what he found. This was for infinitely long strip footings. There's his QU over QS ratio. There's his H over B, and a little bit of scatter, but quite a reasonable straight line relationship with a gradient T. And then for the square or circular footings, he plotted the square root of the increase in ultimate stress against H over B. Again, a bit of scatter. You can see the different symbols for different undrained shear strength, but suggesting a linear relationship between the square root of the stress increase and the H over B ratio. So from this, he determined that the increase in stress was equal to 1 plus T times H over B, as long as the increase in stress was less than that for the granular material itself. And the same increase in stress varies with the square of 1 plus T times H over B for square or circular footings. So using those values, and he did lots of numerical analyses and compared them with Okamura's results and other published data, and found that the T value, the gradient, varied with the normalized undrained shear strength of the subgrade according to a power law. And the normalization he did was to divide the undrained shear strength by the effective stress at the interface, which he called P0 dash. So one of his basic equation then became T, this efficiency factor, is 1.4 times SU over P naught dash to the power of A plus B. And for unreinforced platforms, he found that A is equal to minus 0.41 phi dash minus 0.18. B is equal to 4.2 phi dash minus 3.4, where phi dash are in radians, not in degrees, they're in radians. And then for a particular type of granular material and a specific geogrid, a tensile geogrid, Lees found that T was equal to 2.9 SU over P naught dash to the minus 0.32 minus 0.6. So his A 1.4 has gone to 2.9. A has changed from this to be 0.32, and B has changed from this to be 0.6 for a particular granular material and geogrid combination. So that's his curves. These are for three different platform angles of friction, 35, 40, and 45. Those are my curves plotted on top of Andrew's to show that I've got my calculations right. And these are for the geogrid reinforced platform up here. So I then wanted to compare different methods, partly because I've been hearing this talk of BR470 being conservative. So I won't do that now. So I wanted to do some calibration myself. And first of all, I looked at punching shear, which is this one. So here we're looking at a load applied at the surface under a track, and what is the pressure down here if some of the load is being carried in punching shear. And here we're looking at the pressure on the top of the track and the distribution over a wider area because of the load spread. And in this case, I took 1:2. So pressure, the bearing pressure at the interface for BP1 is Q over A1. So over here, this pressure is Q over A1. For BP2, Q is the bearing pressure 2 is Q divided by A1 plus A2, and therefore the pressure is lower than BP1. But BP3 over here, it's Q minus Q divided by A1. So the pressure here is also supported by these Q values up the side. So what I then did was to compare this BP2 and BP3. And here we are. This is BP1 up here. So that's just during no load spread and no punching shear. We've got 400 kPa all the way down. So this now is for assuming punching shear, but with a platform friction angle of only 35 degrees. And we're looking at different track widths, 1 meter, 800 mil, and 600 mil. So if we're using load spread, that's BP2, we're getting these solid lines through here, okay? Sorry about that. And the load, these are the load spread curves, the solid lines. And then if we've got friction angle of 35 degrees and we use the Kp tan delta method, we get these pressures up here. So these bearing pressures are higher than the load spread bearing pressures. Okay, but that's only for these dotted lines, which are for phi to 35 degrees. If we go to a phi to 40, we've got these short dashed lines, and you can see that those are getting to be very similar to the solid lines. And if we go up to 45 degrees, these are the long dashed lines. These are well below the solid lines, which are for the 1-on-2 load spread. So it's certainly not true that the taking punching shear is conservative when compared to taking a 1-on-2 load spread. These are conservative if the platform friction angle is only 35 degrees, but quite honestly, if you're using 35 degrees as a working platform, you've got the wrong material. You should be using much higher friction angle than that. And then the punching shear method is certainly not conservative. So I was quite happy to have debunked that theory. So I mentioned earlier the work that was done to calculate working platform thicknesses for different piling rigs, for different friction angles. Here we've got 40 and 45 degrees, and for different subgrade undrained shear strength. And these were published. I was lucky to get hold of this data. This is what I am absolutely sure was used to calibrate the BR470 method. I had an independent set of this spreadsheet, but when I put the relevant data into the BR470 spreadsheet, I also calculated these results. So I used it to check that my spreadsheet used to calculate platform thickness was correct. So from that previous version, if I took all the platform thicknesses, all the subgrades, all the different machines, there were 138 different load cases. That was too many for me, so I picked out 19, and I then ran those load cases through the BR470 method, but also through the TWF method, using the spreadsheets I showed you earlier, through the t-value method, and also an online software called Platform, produced by the Nawa geotextile manufacturer. And it included track widths that varied between 0.7 and 1 meter, effective track lengths for L1 between 1.73 and 4.21 meters, effective track length for L2 between 1.1 and 2.8 meters, bearing pressures for Q1 between 120 and 350 kPa, bearing pressures for Q2 between 265 and over 600 kPa, and subgrades from 20 to 100 kPa. So a good range of loadings, track lengths, and subgrades. And these were the results that I got. The top set is for load case 1, the bottom set is for load case 2. The blue curves are the TWF method, the orange ones, the BR470. The gray one is the t-value method using limit state design, and the yellow ones are the t-value method with working stress design. And if you look at all of those, there's obviously some scatter, but I am very strongly of the opinion that there is not one method which is consistently more conservative or less conservative than the other methods. The conservatism varies depending on which load case we're looking at. And I was very pleased that yeah, go on. Is it? Sorry about that. So where am I? Yeah. Very pleased that that showed that there was no specific conservative method. I wanted to include the Nauer method, but that doesn't tell you whether it's load case 1 or load case 2. So I had to choose the critical platform thickness, but the blue line here is for the Nauer platform software. And again, it's not consistently more or less conservative than any of the other methods. So if anybody tells me, or if anybody tells you that one of these methods is conservative, I think they're talking rubbish. They're talking about feelings rather than facts. So I consider it's not possible to say that any of the 4 methods is either conservative or non-conservative across the whole range. BR470 uses the KP tan delta method. The CompuWorks forum uses a 1-on-2 load spread. The p-value method uses the results of finite element analysis and large-scale testing to determine the load spread empirically. So they're all very different methods. There's no reason why they should give the same answer, and they don't, but there's certainly not one which is consistently conservative or non-conservative. With regard to stabilized platforms, BR470 did a review 7 years on in 2011, and they allowed for GeoGrid suppliers to produce their own validated methods. And this is very important because, as I've said, and I'll say a bit more in a minute, each GeoGrid is different. Each granular material is different. And it's been shown quite conclusively that the way that they interact is what's essential, and those interactions are all different. So this has to be done by the manufacturers, and they need to produce a basis of design calculations that is stated and references made to credible research that validates the method. BRE, as I've said, does allow for the use of geotextile. It's very simple. It just takes the ultimate strength and divides it by 2. And that benefit becomes 2D, 2 times TD over W, where W is the track width. But there is now evidence to show that geogrids can do much better than that. It's not even recent. It's been around for 40 years. When load spreading of 45 degrees or more was suggested by tests at Oxford University. And that's been backed up by a lot of work on load transfer platforms to do with ground improvement over piles or control modulus columns, where they work in reverse. And the experience has been gained on a lot of working platforms and wind farms. Sorry, Evie, shut up. No. The wind farms, of course, often require very high and high lift over soft soil. Animals. So there's been a lot of work done, and new tests have been done at BRE in this test chamber, and a 300 mil thick layer of gravel was placed over a soft subgrade. And when it was loaded to 35 kilonewtons, this was what the soil strains looked like on soil displacements. Okay. When that was changed to a granular layer reinforced with 2 layers of geogrid, the load went up from 35 right up to 84 kilonewtons, and you can see the sort of angle of load spreading which was being achieved, which is getting close to 45 degrees. So in their report issued in 2011, their 7 years on review, they allowed for better load spreading, but they left it up to manufacturers to verify and publish what that should be. And several geogrid suppliers have now produced their own methods, which require geogrid but save a lot of platform material. and they're likely to be competitive over soft soils, or particularly where aggregates are expensive, and they're very good with recycled concrete. Tensar have used the T-value method, which can accommodate stabilized platforms, and other geogrid suppliers have this NAWA equivalent, which uses software which is available online. So Andrew Lees and Tensar put some geogrid in some very large triaxial tests. I think they were 1 meter diameter and 1.5 meters high, and tested these and found that the Moore Coulomb failure envelope has significant curvature, and that the best way to describe this benefit in a numerical model was to have an enhanced apparent cohesion. And so the numerical modeling of these geogrid reinforced granular materials can be done, for instance, within Plaxis, using enhanced parameters with an enhanced apparent cohesion. But interestingly, another supplier has done similar tests, large triaxial tests, and you can see they also get a curved failure envelope. So different geogrid, different granular material, but still getting the same shape of response. Wouldn't be the same numbers, wouldn't be the same values, but they're getting the same shape of response. And I think that's very interesting and encouraging. But what we must not lose sight of is cautionary note. Working platforms are frictional, and they're very sensitive to the friction angle. And that's particularly because the punching shear is determined as Kp tan delta. Tan delta is a function of phi dash. Kp is a function of phi dash. So the product Kp tan delta is doubly a function of phi dash, and it's very sensitive. So if you put a conservative values, a subgrade friction angle of 32 degrees, and a weight density of 18 kilonewtons a cubic meter, and these were parameters that were given on for a working platform design that I was reviewing, with a friction angle for the platform of 40 degrees, the platform thickness was required to be just over a meter, 1.02 meters. If you increase the friction angle of the platform to 45 degrees, that came down to 740 mil. If you increase it up to 50 degrees, it came down to 0.52 of a meter. Very close to half of the platform thickness for a phi dash of 40 degrees. So you can see that it's very sensitive to the platform friction angle. This was a real case, and the manager of the office concerned wrote that it was somehow ridiculous for to have a 1 meter thick platform for a medium dense sand, but that is what BRE is telling us. And this is just, I'm sorry, this is just appalling geotechnical engineering, because on the one hand, he's saying that the site was medium dense sand, but on the other hand, he's saying that it had a phi dash of 32 and a weight density of 18. Well, for all you students from that are there this evening, also, if you come to me and tell me that you've got a medium dense sand with a phi dash of 32 and a weight density of 18, you'll hear the rather rough edge of my tongue, I'm afraid, because that's just nonsense. The medium dense sand does not have those sort of parameters. If we change phi dash to 36 and we change gamma to 20, which is much more what you would expect for a medium dense sand, look at the platform thicknesses now. Even with 40 degrees in the platform, we're only needing a nominal 300 mil thick platform. So it is very sensitive to the angles of friction that you're using, and you must use sensible parameters. If you put very conservative parameters into BR470, it will give you a very conservative answer. Don't blame the method. That's all to do with the data that's being put in. So I mentioned already David Cork. He did a review of BR470 in about 2009, published a paper in geotechnical, in ground engineering, and showed there that it was very important to use proper values for the subgrade shear strength and for the platform shear strength. This more recent paper in 2021, also in ground engineering, is reporting on some tests on very small diameter plates in a centrifuge, but he did careful analysis, careful testing to show that the scaling was appropriate. And they measured friction angles, according to these plate tests, of 58 degrees for one, 58 degrees for another. So those sort of friction angles are actually available, can be demonstrated by testing, but David Cork's recommendation is that those are too extreme, that he would not recommend going above 50 degrees, but even then, that's a very high friction angle and very useful. Here's the test result, a whole range of test results with different ratios between the plate diameter and the maximum particle size. And you can see that they're all up in the 50s. There's nothing even anywhere near that. In fact, they're all above 57 degrees and they're in quite a narrow band. So, TWF manual also points out that BR470 is very sensitive to the input parameters. So in practice, the analytical method has proved extremely sensitive to the values used for the platform material and the subgrade, the same thing that David Cork had said. It's limited, BR470 is limited to cohesive subgrades between 20 and 80 kPa, although that's a very useful range, and you need to take great care where if you're going down below 20 kPa. It only allows two layers, the platform and the substrata. So if there's more than one layer, you have to take the worst case. So it is conservative in that regard. And if you want to use geosynthetic reinforcement, the method of analysis is very simple, and there are probably better ways of doing that analysis. So in conclusion, looking at the comparison of the 5 different methods that I did, none is consistently conservative or non-conservative. The conservatism varies from one case to another. The benchmarking data which the FPS used creates, I believe, a very good standard, a baseline under which, against which other methods can be calibrated for non-stabilized platforms on cohesive subgrades. Methods which suggest thinner platforms are potentially unsafe and need to be calibrated against the dataset. It appears that the use of strength factoring of the platform in the T-value method may be affecting some results adversely, some of the conservative values there, and Andrew Lees was going to look at that further. A similar exercise for granular subgrades I've got in hand at the moment, and we'll be publishing the results when they're available. I've still got to do the calculations with the TWF method and with the T-value method, because Andrew Lees published a later paper covering granular subgrades. But please remember that the loading factors in BR470 are empirical in nature. There is nothing fundamental about those loading factors. They are not factors of safety. They are not partial factors, and they cannot be taken out and used within other methods to produce working platforms of lesser thickness, which I have seen done. That's a big no-no. For stabilized platforms, unfortunately, there's no data set available against which to calibrate any design methods. So suppliers are working on their own methods, and they'll need to verify these in a manner as robust as that was used in BR 470, with which we've had 20 years of experience now, and it would seem to be very good experience. But the calibration would need to be done with full-scale testing, laboratory testing, and numerical modeling in an appropriate way. So that brings me to the end of that. But shall I try and run these videos?
Because they're instructive. Yeah, hang on. I can't. I've lost my microphone.
I can hear you.
Oh, good. Yeah. Yeah. Try.
Right. Okay. So, right.
Yeah.
I'm going to stop share, and then I'm going to share. Okay. Are you seeing the right thing?
Not yet.
Are you seeing it?
No, not
Oh.
yet.
Sorry. Okay. Wait a minute.
Yep. Okay.
Right. So this was in Brisbane in about 2017. And you can, yeah, you can see there were two people walking there and some surveyors. And lo, here it comes, crushing down. So really very, very lucky that nobody was hurt, but that was more by good luck than good judgment. Okay. I'll just see if I can run this one. So this was in November of 22 in Frankston in Melbourne. And the amazing thing here was that this crane crashed down on the roof of a psychiatric unit. Over 70 people were evacuated from the building because although it had a tin roof, underneath the tin roof, there was quite a significant concrete structure. There's the people being evacuated. So they were real people. And you can imagine what might have happened if that had been a lighter structure. Okay. So, and now I'm going to try something. Just going to try one more.
We can see it. Yeah.
Okay. So
Yep.
this is down in New Zealand, and they seem to be lifting off a steel beam from a bridge for reasons that I don't know. But you can see a crack there, just behind the gentleman in the blue hat. but this is one of these sort of case one loadings. Things are happening, but you can't put the load down fast enough. And camera, but so the beam was obviously being lifted. So there's another crane on the other bank. They're obviously trying to bring the beam to this bank, but before they could do so, crack opened up, and lo and behold, wood. Okay. So, I can tell you more about those things if anybody wants to know, but I'll stop sharing now and let you yeah,
Okay.
fire away.
So Stephen, that was very, very interesting. We certainly have some minutes for a question or two. Would anybody like to ask a question? Yeah, Phil.
Yeah, thank you, Stephen. Your presentation was fantastic. Just a couple of comments really, and the first one was about the last video. Slope stability analysis can be equally important as the actual platform. I worked in the Waikato and Brisbane, and certainly if you're using big cranes next to creeks or rivers, you have to also do the slope stability analysis as well as the platform analysis that you've talked about. Second comment.
Can I'd just like to add a little, if I may, Phil. What I was told by somebody in Brisbane who owned the crane company, it was interesting. They had actually done load tests. So they'd actually loaded up each of those pad positions to the full load. And that in itself is very interesting because, of course, for a relatively small pad, you've then got a three-dimensional failure surface. Whereas if you notice with the two pads loaded, you could see the crack extending between the pads. It was actually a very two-dimensional failure, which has a lower factor of safety. And so there were a combination of things that led to that failure. Yeah, thanks.
And the second point is on conservative design methods. I would always go for something conservative. Quite often, the problem you have is the material parameters that you're putting in. Normally, the actual platform itself, you've got no idea what phi is because you haven't got very good testing. And sometimes what's underneath that for a working platform can be either anything from nothing, no idea, to very poor because people tend not to do investigation and lab testing for working platforms. So anything which is conservative to me, I would always go.
Yep, agreed.
Thanks, Phil. But anyone else? We've probably got time for one or two more questions. If anybody would, yes, please. Right.
Hi, Stephen. Thanks ever so much for the presentation. That was very interesting. My question is, I've been approached recently with regards to piling mats, which is close to my heart because we do piling, and the use of bamboo stressed platforms. What is your opinion on that kind of technology, the use of that as a platform?
Bamboo.
It's a pre-stressed bamboo plank.
Okay.
Have you had experience of?
Well, I'm aware bamboo has very high tensile strength. It's a remarkable natural material. It grows in my garden. I haven't seen any numerical thing, but if somebody's done some testing and can produce a characteristic tensile strength for the material, and I don't see why they shouldn't. It might, as a natural material, you'd expect its characteristic strength to be on the conservative side because of natural variation. But there are rules for the statistics that can be applied. I would see no reason why, in principle, it can't be used. I mean, fascines, I think, were used by the Romans, which are natural material earth reinforcement. So that it's been around for a very long time. Yeah, I'm all in info. Don't tell Mike, because he would prefer to sell you some plastic. But in principle, see no reason not to.
Okay, thank you very much. Thank you.
Okay, maybe one more if anybody else like to ask, because I don't think curry's arrived. Has anyone noticed? Has the curry arrived? Sorry, this is a very important question we have here, Stephen. Has the curry arrived? So
I can smell it.
well, but I can't. That's the problem. Yeah, we'll sort that a bit. Yeah, go on. Sorry. Okay, yeah, David, please. David, with that. So David is our country representative to the ICE-JLA. To ask a question, but just be careful because he's a watery guy. But he just
Yeah, well, thank you for saying that. I mean, actually, I'm an irrigation engineer, and a lot of our projects are on soft clay soils. So it's very interesting to me because our structures usually have to be piled, but also our approach roads also need some support before we just put in the soil. Now, I would have imagined that if you want to put down a gravel base for your crane, you'd want to separate it from the soft soil. So would you be putting in a geotextile between the gravel and the soft soil? And where would you put the geotextile? Would you put it towards the top of the gravel, or would you put it above the geotextile if you were using a geotextile?
Just on that, okay. I've got Mr. Dobie holding the microphone, so I've got to be very careful what I say here. I think the two are slightly separate. So geotextiles are commonly used as a separator between the coarse granular material for the platform and fine cohesive material in the subgrade. I think that's a very suitable use for geotextiles and will probably help to keep the granular material with its appropriate friction angle, and where the materials are expensive, having a geotextile separator I think helps you to be able to recover more of the granular material, maybe to use somewhere else on the site. The geogrid itself needs to be within the granular layer, usually near the bottom, but it needs to be certainly to have granular material above and below it. Is that a suitable answer?
Yeah, no, David's nodding appreciation for that. No, thanks very much. But no, Stephen, a very nice summary between the two sorts of materials. Well, I think we'll let you rest now. And is it dog management you've got to sort out over there? We're not totally sure what you were shooing away from behind your seat.
Oh, but my wife has been out, and therefore I've got two dogs.
Two dogs.
I've got one of whom I brought from Australia. She flew here from Australia, but there were people. They're very good guard dogs, and they were aware that somebody was wandering around outside. But it was a bad moment for me.
Okay, well, it was a very nice sort of moment of your presentation when you disappeared off the back of your seat. But no, But let me thank you again. I mean, there was an awful lot of material in your talk there, and I think some of your comments about conservatism and soil properties, and if you like, not mixing the two things up is really important as well. And there's lots of good information there. I hope actually working platforms is a very good topic for students to look at, and some of them might be interested to do that after watching your talk. We have quite a few students here tonight and many more listening in online. So I think there's some excellent background information there, and I thank you very much for putting together a lot of information. Perhaps we just have one more round of thanks for this evening.
Thank you. But Mike, anybody in your local association, if they want more information from it, if they want a handout of this presentation or with the equations and things in, if they contact you, you pass it through to me.
You know, I will contact you about that, because in fact we will, if you don't mind, we just like to make normally a PDF 2 slides per page of the slides you would like to provide, and then we'll circulate that to the people who are attending. Yeah. Yeah.
And I can provide more detailed stuff. I mustn't provide copies of BR 470 or the TWF guide because they're copyright material. But my stuff, I'm happy to, if students want to know more, want to do a bit of research on it, they can get in touch with me. Happy to work with anybody.
Great. Well, thank you very much again. So please, you can now relax and enjoy your time zone is the same as ours, I think. So
yeah, I'm going to have my dinner.
Yeah, go and have your dinner. Okay, thanks, Stephen. Okay.
Thanks very much. Bye-bye now.
Thanks to Mr. Mike and Mr. Bill for guiding the session, of course. Once again, thank you to all the speakers for your excellent presentation. Before we finish this event, please fill out the attendance form to claim your certificate using the bullet links in the chat or the QR code. For business students to claim your SAT, please make sure to fill out the attendance form. Ladies and gentlemen, we have now reached the end of our events. Once again, thank you for the participation. We hope to see you at the next event. At last, good evening, stay healthy, and take care, everyone.
Are you on next week meeting? What they would see? I think it'll be it's around 6 p.m. I think. Might go for Tuesday. I'll check out mine.
We're going to discuss about the next.
Yeah, this is
Yeah.
I don't know how it's all working.
So we're not going to discuss that now.
It's clear.
Okay, sure.